Okay, can you hear me now? You should better hear me now. All right. How frustrating. Sorry, folks. Buggy software. Let's start over. Okay. Thank you for letting me know, folks, on the chat. Yep, okay, great. All right, let's start over. Welcome to the Friday lecture, take 2. And we'll move to the slides. Apologies for that audio issue. We're off. And that was a bug in OBS, which is the streaming software. For whatever reason, I just needed to disconnect and then reconnect the mic, and now it's happy. Let's go to the slides, the admin slides. Okay, so first of all, assignment 2. Make sure you check the deliverable dates. There's one little catch, and that is that D2F, you might have thought that was going to be due on Monday, but that Monday is Labor Day, so it's actually due a little earlier. Don't stress about that. It's not a huge amount of work for D2F, but it is due on the Friday, not on the Monday. So just always make sure you're checking the due dates for all of your deliverables. Another point is for D2E, which is due this coming Monday, you're supposed to develop a test. And if you've been watching the lectures, you'll know that we've been spending a lot of time on tests, and you'll also know that it's really easy to write a test that's not that helpful. And what you're expected to do for D2E is actually write a decent test. I write the test very, very fast in the lectures, and they're just giving you examples, and I often give commentary to you on the shortcomings of the tests that I write in the lecture, which are very, very quickly written. And the point is, these tests that I write in lectures tend not to be very exhaustive. They're clearly not exhaustive, which means that you could write an incorrect program that would still pass that test, because that test is only checking a small part of what the program could possibly do. We actually call this, in computer science, we call this coverage. The coverage of the tests I write in class, because I'm writing so fast, is very, very small. You're expected to have your test to be reasonable, to have a bit more coverage than the sort of stuff I do in class, okay? So it's not a matter of slapping out one thing and checking for that one thing. It's a matter of thinking through what are the important cases and what should I be testing for here, and being a little bit thoughtful about it. If you want, you can look at the sort of tests that we write for the assignment, and they're not perfect either. They don't have perfect coverage. And in fact, I just saw a Piazza issue for the 1140 assignment where someone thinks they found an error in one of the tests, and I'll check that out later. All right, so what else we got here? That's pretty much it. Don't forget, the major deadline for this class is week 9. And one of the things that you're encouraged to do is to start making sure that you can put it together, all the things that you need for that deadline, including making sure that you're producing jar files. Now, there are instructions online on how to do that. Make sure that you can produce a working jar file, which is how you're going to be tested in the end. Make sure you use the labs that are coming up to work through things with your tutor. And if you're having issues with your group, make sure you talk about them with your tutor and talk about them to each other. Don't forget, a large part of this course is about learning to work as a group and learning how to resolve problems in a group. It'd be a very strange group that didn't have problems. Most groups experience some problems. It's a matter of how well you deal with them. Okay, let's move back on to where we left off. And where we left off was with lists. We looked at 2 different ways of implementing lists. Hopefully you can all remember this. The 2 different ways we implemented lists were, what were they? Can anyone write it in the chat? There are two ways we're doing it. We're implementing a list with an array list and a linked list, okay? And I talked about, and we got up in the code, we got up to the point just about where we're going to do the list reversal. I'm going to skip through this here. I wrote a new animation here. Major deadline. What do I mean by major deadline? I mean the deliverable for the assignment, right? Let's just go to the deliverables page. Let's just go through here. Deliverables, deadlines. Sorry, I'm not there. Schedule. Okay, so all right. So that. Sorry, what did it say? Okay, so. All right, so that was bad. That's a mistake in the slide. So yeah, I probably scared you. There's not a major deliverable in week 9. Okay, the major deliverable is in week 11. There, but okay. So F is due in week 8, and G is the big one, worth 13 marks, and that's due in week 11. So yeah, thank you for questioning me on that. I was just going off of my slide, which was clearly not correct. All right, so hopefully I've clarified that for you on the chat there. The big deadline I talked about earlier is in week 11. But the real point that I made on the slide is check the deadlines. Okay, so go to go to the webpage and make sure that you know when the deliverables are. All right, what I wanted to do right now was to go and revise the recursive linked list reversal. We want to reverse this, and what I normally do in a live lecture is I actually get people up here with pieces of paper which are pointers. Next and first and last, and I have 4 people being the list nodes, and I have someone being the first and someone being the last, and I get them to actually do it on the stage. It's kind of fun. We do it every year, and but we can't do that here now. So I've created a PowerPoint animation, which is not half as good, but hopefully we'll get the idea across to you. The question is, how do we reverse this list? You can see the list on the screen there. We want to reverse it, and we're going to use this recursive technique, which I said to you that we can use a recursive technique. So how does it work? Well, the basic idea is you got to think about one of the key things you do with recursive methods is you have this suspension of disbelief. You assume that you've already got the thing working, and then you use that solution in your solution. That's where it's recursive. You use your solution in your solution. And yeah, pity you learn that. I know it sucks that we're not face to face. To me, I get so much energy out of being in the room and talking to you all. I enjoy chatting with people before and after the lecture, and I'm finding it really hard doing it like this psychologically. And I know that a lot of people learn better when you actually get to see stuff on stage. So sorry about that. This is one of the things we're going to have to make the best we can with what we've got, and hopefully this PowerPoint will get the idea across, even if not as fun as doing it in person. So what we're going to do now is we're going to say, okay, we're at node A, and let's just imagine somehow that we've got a recursive reversal working already that can reverse the rest of the list. Okay, so somehow we've reversed the rest of the list. There it is. Okay, so the rest of the list has somehow been reversed. What do we do now? Well, it should be pretty obvious what we do now if we did have that working. Okay, so if you just believe for a moment that we have this thing working, so notice that this part here, those 3 there, have been reversed here, right? Okay, and so this here represents the reversal of those parts there. So if you had that, how would you put A in the right place? Well, it's pretty obvious. You really want A now to be the last if you're reversing, and B would point to A, right? And so So B points to A, and the last now goes to A, right? And if you just draw that nicely, you end up with this. So you reverse the list. Okay, so let's just step through this case by case. So I said let's just pretend we knew how to do that. Okay, let's try and do it now. Okay, so here it is. We're going to try and reverse these 3 here. Here they are. We're going to try and reverse them. Let's apply the same trick. This is what recursion is all about. We'll apply the same trick. And so we're going to take B, and then imagine we'd reverse C and D. There they are. They've been reversed. Now it says D and C. And the first points to D, and the last points to C, because we flip these ones around. Okay? So imagine, suspend disbelief, just imagine we can do that. How do we reverse the whole list, given that we've managed somehow to reverse D and C? Well, it's pretty simple. Again, we just make C point to B, and then we move the last to point to B, like that. And unfold it, and we get this. We've reversed the list. Okay? Do it one more time, and let's just see how we actually reverse this, which was the part that I said just imagine that happened. Well, let's actually do it, and we'll apply the same trick. So we're going to say, let's separate this out. There's C, and there's the other list, D. Well, it turns out it's trivial to reverse D. Why? Because there's only one element. Okay, D's a one element list, so it's straightforward to reverse D. And so we have C here, and we have D reversed, which is trivial. And then all we need to do is apply the same trick. So now we have this, and then we unwrap it. Okay, so working backwards, it should be very easy to see how we reverse these 2 elements. Okay, just step this through, rewatch the video if you need to, and you can see how we reverse those 2. If you could reverse those 2, it becomes easy enough to see how we could reverse these 3. And if you can reverse those 3, you can reverse those 4, and so forth and so on. And that is a recursive solution to list reversal. So what we're going to do now is we're going to go and code that up. So let's go back to where we left off. Wrong thing. Linked list. Okay, this is where we were. Let's run the tests. Where are we? Run the tests. We had tests here, so I'm in the wrong place. This is our next module. We're at A02. and we're going to run our list test here, and right click on it, run the test. And someone asked, will there be any more homework? We don't have homework questions for a lot of the more advanced stuff, I'm afraid. That's something we're working on. It takes a lot of time to write those homework questions, so we don't have any. But what we will have, what I will be releasing to you soon, is a practice exam, which is like the MSc, but for the final. And so that will cover material right up to the end of the semester. So that might be useful to you in terms of homework. It's not homework, but it's a practice exam with tests and everything. So it's like the homework. All right, now let's get on with this. We're going to write this reverse method. So we passed all the tests except reverse. Notice that? Okay, so now we're going to write the reverse method. And what we can do is we're going to write up here in a moment. We're going to introduce our own little recursive method, okay? So we'll write a private recursive method up here in a second. But let's just first of all do this. Now the first case, let's just deal with the case whether it's an empty list, right? So that's easy to do. Let's just say if first is equal to null, then there's nothing to do. We just return. Okay, there's nothing to do with the empty list. Then return. Okay, and then otherwise, and if you'll have to in your head at least go back to this PowerPoint, right, and remember what I did there. What we're going to do is we're going to say last is equal to first, and then we're going to say first is equal to the reversed list. Okay, so we're going to write this method in a minute. Just imagine we already had this recursive. Okay, we don't have this. We haven't written that yet, of course. And then finally, we're going to make that whatever was last, whatever is last, its next pointer has to be null, which symbolizes that it's now the end of the list. And I'll just show you that to you again in the PowerPoint. Okay, so you see here C is last, and its next pointer points to null. The ones that point to nothing, that's pointing to null. Okay, so we make the last point to null. All right, let's just go through that code one more time, again with references. So last is equal to what was the first, and the first becomes whatever you got from reversing the list. Let's have a look at this again. Look at one of these examples. So there's first and last. So the last becomes what was the first. There it is, it's A. And first becomes whatever we got back from the recursive reversal. There it is. Okay, hopefully that makes sense. So the code I'm writing here should match very closely to what you saw in that demonstration via that animation. So now let's write this recursive reversal thing. I've got a question here, I think. What is it? Would it be better to just have only one condition? If it's not equal to null, then yeah, you can do that. Of course, that's a good suggestion. Let's do that. I like writing your code in here. This is what I miss so much about the live lectures, because in the live lectures I get a lot more of your feedback. Let's just do exactly what Lewis suggested. Here it is. Oops, if I can only type. Okay, so someone said, man, apologies. All right, so someone suggested, Lewis suggested this in the chat. Just do that, which is cleaner and simpler. All right, so as long as the first is not null, I know the reason why I write it the other way is because it's really clear what I'm doing. I'm saying, okay, we've got to null this, there's nothing to do. So I put the return. This here is implicitly saying the same thing, and it's cleaner and simpler, but it may not be as obvious what I'm doing. Okay, so but still, great idea. So that's why I've implemented your idea. Now I've lost what I was typing before. Okay, so private LL, which is our LLN, which is our linked list node, which we defined just above. It's going to return a linked list node, and we're going to say recursive. Did I already type this? Why is it? Oh yeah, it's. I was wondering how it was doing the completion. It's doing the completion because I'd already typed it down here. Okay, and then we'll say LL old first. Again, I might write a comment here for those of you who get the code. Okay, there's an animation in the PowerPoint which will help you understand this, right? So if you come back another time and look at this code, you can look at it. All right, so now the first thing to do is if the old first, the thing that it points to is null, then we just return it, okay? Because that means that we're at the end of the list, all right? So if we're at the end of the list, the base case is that there's nothing in the list. LN is linked list node, and it's defined just up here. We did this in the last lecture. Where's my mouse? Scroll up. There it is. This is our little class we wrote before. Linked list node. Okay, LLN, linked list node. All right, so come back down here, and then what we're going to do is we say, okay, if the old first dot next equals null, what that's saying is that we had a list, and the first oh, thank you, in the parameter list, yep, LLN, yep, thanks. Right. So if we had a list and we went to the first node in the list and what was next is nothing, then that means we've got a single element list, right? The first thing in the list is the last thing in the list, then it's the last one, okay? So we can just return what we had, because reversing a single element list is straightforward. Return old first, right? Okay. Otherwise, oops, typo, else. Otherwise, we want to establish a new prior. That is, we need the thing before the one we want. So we're going to call it else LLN new prior equals the new prior is the whatever came after the first thing in the list. Okay, so in other words, the thing that we're pointing to, the first guy is pointing to, that will actually go and point to us. So what was previously the next, in the future, will be the previous. So we need to know what was before us, what will be before us, and whatever will be before us is whatever was after us in the past. Let's look at the slide to make that a bit clearer. Okay, so this B is going to be before us in the end. There it is there. So it's before the A, right? And so, but right now, the B is the next, okay? So we're going to call this thing the new prior because it will be the prior to A later on. And the new prior is obviously A's next, okay? So whatever comes after A will in the future be the thing that is before A. And that's what you see right here. So let's go and keep writing. New prior equals for old first dot next. Okay, makes sense? That's B in the example I just went through. All right, and then the LLN first is going to be equal to what? Remember what first is going to be equal to? Let's go back and look at the PowerPoint. What's going to be first equal to? It's going to be equal to, take all this stuff here, reverse it all, and whatever is the beginning of that will be our first. There it is there. Okay, so it's going to be equal to the recursive reversal of everything left. Right, so let's do that. First is equal to recursive reversal of old first dot next. Old first dot next. Is that right? And then, yep, which could also be written as new prior if you want, if that's more obvious. Right, either way, they're the same value. Okay, so and then once you've done that, okay, we've nearly done. What was the other thing we had to do? So we now have to make this thing point back to us. Okay, so that is the last here. This was the last. B was the last. After we did the reversal, B was the last. And now it needs to point back to here. Okay, so so we need to make B point back to A. And we remember what B was because that's the new prior. So we say new prior dot next equals old first. Okay, so we've flipped it around. And with that, we can just return first. There it is. So that should work. Let's see if it does. All right, what's going on here? There we go. Let's see if it works. Excellent. We've just implemented recursive reversal. Although, remember, I just said it works, but what we really mean is that it passed our little tiny set of tests, right? And let's just quickly see those tests. Where is it? Link test. There it is. List test. So you can see the tests there. Where's remove? Where's reversal? Okay, it could do those tests, all right? So what we've done is we've implemented a solution that at least passes those. I mean, I believe it's correct, but just to be completely precise, we don't know it's correct. All we know is it passes the tests. All right? Any questions? If not, we can move on because we're kind of a little bit behind here. Yep, let's move on. If you have any questions, now's a great time to shout. Oh, dang. Have I really done that? I left the slides out. That's a bummer. All right, no worries. What I'm going to do here is I'm going to open up last week's slides, last Monday's slides, and go back to where I was. Oh, that's embarrassing. All right. This is where we're supposed to be at. I didn't realize I didn't put them in today's slides. They should have been there. All right, so this is the unit we're up to. We're up to J15, which is exceptions. I promised you would do exceptions. So now we're going to do exceptions. Before I jump in here, I wanted to remind you about the control flow. You've all hopefully now remember control flow and what we have in imperative programming. And can anyone say what the key things in imperative programming are on the chat? What do we have with imperative programming? You can remember the Jacquard loom was a bit of a clue. We have sequence, selection. What's the last one? Can anyone remember? What we're going to do now is we're going to show a variation on control flow. I don't see anyone. Okay, here we go. Perfect. Iteration. Yep. Sequence, selection, iteration. Good job. You guys are remembering stuff. Very good. Okay, terrific. Sequence, selection, iteration. Okay, so sequence, selection is a branch, iteration is the loop, and we have while loops and for loops. All right. Now the thing that we did one more thing that violated that. What was was completely different to that? What was it? What was the other thing that we did? The other control flow that was bizarre, that was different to this. Can anyone remember? We did another control flow that was completely different. GyroFX is the clue. Whoops. We've got two mice here. Wrong mouse. No, there's not one more. What was it? It was when we did event-driven programming. Okay? With event-driven programming, instead of going sequence, selection, or iteration, we just suddenly branched to a different place. Yeah, we used lambdas to specify it. That's right. But the control flow was event-driven. It says when, like the mouse gets clicked, suddenly jump from wherever you are to over here. Execute this code right now. Okay? And that's event-driven programming. And so if you can remember that, yeah, events, right? So if you can remember that, exceptions have a little bit of a relationship to that, okay? Now, exceptions are another strange control flow, but they're designed for error management. One of the big problems is if you have a very big program, what you need to be able to do is handle the case where something erroneous happens. And you can think about the erroneous things that happen. I've written a bunch of them on the slide here. You can see there are things like someone says, like imagine in GitLab or maybe in a word processor or something, you say, I want to load this thing here, and it's not there, okay? That's an error. In that case, because the person who's using the program gave the wrong information, right? And they loaded and the thing wasn't there, right? That's an error, okay? Sometimes they're errors made by the programmer, but other times they're errors that arise for things that had nothing to do with the programmer, that had to do with the outside environment, such as the user giving a file name that doesn't exist. Okay, so these are the sorts of things. Or the user might give an input for a number of times to execute something, and you may have had an array that wasn't big enough. Then you get an array that's accessed incorrectly. Okay, these are all things that are errors of certain sorts. Okay, the question is, what do you do? Well, you could just have the whole program crash. That's not so nice, right? And so some languages, including Java and C++ and a handful of other languages, have this notion of exceptions. An exception is an exception to that control flow. You all understand what the control flow is. You're going to break that, okay, because something exceptional happened. All right, and so the way they work in Java is that we have exceptions that are thrown either implicitly. That means we did a null pointer exception. You've probably seen null pointer exceptions in your coding. So an implicit exception is when something like a null pointer exception happens because not because you said please do an exception, but rather you said please access this thing, and that thing was null. Okay, that's implicit. But you can also explicitly throw an exception. Now, can anyone guess why you'd explicitly want to throw an exception? Why on earth would you want to do that? Okay, so you understand that exceptions get thrown. So on the chat, see if anyone can think of a reason why you would ever want to explicitly throw an exception. I'll give you one clue. We're going to go and do it in a few minutes. We're going to write it for a good reason in a few minutes. And I mentioned this in Monday's lecture, actually. Okay, but it's obvious how they happen implicitly. That is, you do something wrong, like you do a divide by zero. Yeah, but what's a specific reason? What can anyone think of a concrete example? Maybe with respect to the stuff we've already coded. Yeah, look, I'll spell it out. One example is if you're implementing the thing like we're implementing a linked list, which is exactly what we were doing a few minutes ago, and you were implementing a list, and someone tries to access something outside of the list, says, please give me element number 6, and there's only 4 elements in there. What do we do? They've given us a really silly request. The right thing to do is to throw an exception, say, hey, out of bounds exception, right? So we're the one generating the out of bounds exception rather than the Java runtime. So that's an example of us explicitly throwing the exception, and we're going to do it soon, okay? We'll add our linked list implementation, which we just went through, and an array list did not do that, but we'll add that in, and we'll have it do that soon, okay? So now, very important, exceptions are propagated from the callee to caller until a matching handler is found. Callee means the method where it happens, and if an exception happens in this method and there's nothing to catch it there, then it gives it to the thing that called it, and it will see if it can catch it, if it can't catch it, and so forth. And ultimately, if it gets to main, which is the main method, and it can't catch it, bang, your program crashes. And you've seen that. You guys have seen that when you get a null pointer exception, your whole program crashes, and that's because no one caught the exception. Okay, but you can catch the exception, and we're going to go through some examples. Okay. Checking for strings and integers is a great example, and you could use that in your assignment, or even in the exam, for example. If they gave you, if the tile number thing was supposed to be a number and it wasn't, you could use an exception handler or something like that there maybe. All right, so now what you need to know is that Java has this so-called catch or specify requirement, and there are 3 types of exception. Okay, so it depends on 3 types of exception. There's an error. You should never see an error. Error is like really bad, and that shouldn't happen. That's when stuff goes wrong inside of Java. A runtime exception, and they're common. And an example of that is a null pointer exception. Okay, and they're ones that happen when you write code that doesn't do the right thing, right? So like a runtime exception because of null pointer exception, divided by 0 perhaps. Checked exceptions are ones that as everything else, and that tends to be ones where you do something which everyone knows could be wrong, right? Could be a problem, and an example of that is opening a file. Okay, so it's kind of well known that opening a file could cause a problem, and so Java says for all those kinds of exceptions, you have to explicitly write a try-catch clause around it. And you've seen me do that every time I've written code in the past in this course that accesses a file. I've gone and written this try-catch stuff, and I've said to you, I'll explain that later. Well, right now we're explaining it, okay? And that's because whenever you do something which could throw an exception that is not an error and not a runtime exception, then you must handle it somehow, okay? And it requires in that case that it's either enclosed by a try statement with a suitable handler, or you say that this method that it lives in could throw the exception. Okay, so you're kind of announcing stuff could go wrong here, someone needs to handle it, and someone must handle it down the stream. Okay, that's the rule. Okay, that's the catch or specify requirement. Either you catch it or you specify it. And so it looks like this, the syntax looks like this, you write a try, and the actual thing you're interested in sits right here. That's where you open the file or whatever it might be. And notice you can have multiple catches. You can have a catch for different kinds of exceptions, because this code here could be quite complicated. It could throw different kinds of exceptions if you wanted. Or you can just write this exception. That there is a subclass of that. So you can simply write this, that will catch everything. That there has been quite specific, because you might want to say, okay, if they did an arithmetic exception, I'll print out the following error message, or I'll just assume the answer is 4 or whatever, 42 or something, and carry on. Or if something else happens, like, I don't know why this happened, and you might just put out an error message and stop the program, for example. Okay, so you can handle different errors different ways in the context of one piece of code if you want. And then importantly, you have this thing down here called finally. And what's interesting about this is this code is guaranteed to be run no matter what happens. So no matter whether that code there generates an exception or not, the finally code is guaranteed to be run. Can anyone guess why you'd want to have finally code? Can anyone guess? I've given you a big clue right here in my comment. It says, if you need to clean up, what might that be? Well, I'll answer that myself. Yeah, perfect. Someone's already said that. Adam's already said closing files. That's a great example. The way operating systems tend to work is that they have a limited number of what we call file handles, which are associated with every open file. And so it's actually important whenever you open something like a file or a stream that you close it afterwards. And so if something went wrong and up here you did an open, somewhere up here you want to make sure that no matter what happened, you actually close that thing you opened so that you don't end up leaking file handles. All right, so that's a great example. What about garbage collection? You'll need to be more specific. I can tell you lots about garbage collection, but I don't think it comes up here. Maybe it does, but I'm not quite sure what your question is. So maybe you can just tell me. I can see a question in the chat there. I'm going to publish your mini quiz poll. There it is. I just published it. And if Darren asked me more specifically his question, if it always runs, why do you need a separate statement for it? What does that mean? You need to say, what's the it in that sentence? I don't know. Sorry, I'm reading the chat questions here. All right, I'm going to continue with the code now, and I'll come back to the chat questions, but there's not enough information there to answer either. And what about garbage collection? I don't know what your question is really. And the other question about if it always runs. The finally, I see. If it always runs, the reason why you need a separate statement for it is because the exception handling could take you to a different place in the code. And what finally does is make sure no matter what happens, it always runs that. Okay, so it's a way of assuring that it runs, and because otherwise it might it could skip over that code. And hopefully in this example I'm going to run now, we'll illustrate the point. Okay, so let's get moving on this. We're going to create a new package. File new Java package J15, and file new class, new Java class. What we're going to do, folks, I'm going to write a little toy class here to demonstrate the ideas. Then what we're going to do is dive into the linked lists and make those tests. Test whether the functions are handling exceptions correctly and fix the implementation so they actually do exceptions in the right places, like when someone tries to access, do a get on one of the lists where the index is outside of the range and stuff like that. We'll do that in a minute. All right, so for now we're going to write a very simple little toy program. Exceptions, there it is, add it to Git. All right, we're going to first of all write this. And we'll write, just partly to answer the question from Griffith there, we're going to be very explicit about what we're doing. We'll say, so you can see where the control flow is going. Hopefully this will answer the question. Start of main, and then we'll write another one at the end here. And we'll say end of main. I'm just putting these here so that when we run the program, it's kind of really obvious how the program is flowing, right? And then what we're going to do here is we're going to call a little method here called exceptional method. Like that, okay? And then we're going to write ourselves this little method here. All right, now what we're going to do is we're going to start off by doing something very simple. For no strong reason, I'm just going to do this one. Date D equals, what is it? New date. Okay. And there's nothing special about dates. It's just a way of generating a date object. And then what we're going to do is going to print out the date, right? So that's fairly straightforward. D dot, I think we just do that, right? Yeah. Or toString. We explicitly call the toString method, I guess, just to make it more obvious what we're doing. I don't think we don't need to say toString, but we'll do that explicitly so it's really clear what's going to happen here. All right, so let's just run this. Actually, we're going to do the same. I'll punctuate this with the same messages. End of method. Start of method. Okay, like that. And then we'll run this program and it should do nothing exciting. There's no exception handling or anything in here just yet. but we're just going to run it. Okay, so you can see it just what you expect. It starts off by going to the main method, then it goes to the start of the method, then it prints out today's date, then it goes to the end of the method, and then goes to main. All right, so there should be no surprises. Okay, and then right now what we're going to do is what we're going to do here. Imagine if we do the following. Right, hopefully you can all see what's going to happen now, like that, and you should see, you can, all right, hopefully everyone can imagine what's going to happen. The answer is that we'll get a null pointer exception because we're going to do toString on a null object, so it should blow up, right? And you're familiar with this, you've probably done this accidentally before. Okay, see that? We've got a null pointer exception, all right? Notice here what happened, that we got into the main method, we got into the start method, then we have the exception and nothing after that, right? Now, so what we're going to do now is add in a try-catch clause here. Notice the exception we've got here is a runtime exception, null pointer exception. So we do not need, in this example, we do not need a try-catch clause. We're putting the try-catch clause here to illustrate how exceptions work. But notice that Java was quite happy with me writing this code without the try-catch clause. Whereas if you do a file open, it'll say, no, you can't even do that until you put the try-catch clause there. Okay, but the one I'm doing at the moment, we're putting it in here kind of for fun, for illustration purposes, rather than because we're forced to. Exception E, and then what we can do here is we can say we can say something like this. We can say what I'm going to do here is write this. Right. So what's going to happen is if we get an exception, it should execute this code here and print out the E. Okay. Now let's just execute this. Where are we? Run. And you should see it now gracefully handled. And now look at what happens is we go to the main, then we go to the method, then we get to our little exception, which we wrote ourselves, our exceptional handling. So this thing has failed. It's caught it, and it has then continued and gone to the main, back to the main, end of the main method, and then back to the end of the method, and then back to the end of the main method. Okay. Why doesn't Java allow you to write a file opener without it? That's because it's one of the fundamental rules of Java that you. Let me show you. Because of this, it's the rules. Maybe Lewis asked the question about why you can't do it. Because that is a checked exception, and I suppose the answer is it's kind of philosophical rather than anything else. It's a matter of programming language design. The idea is that we want programmers to be very conscious of code that could cause the whole thing to fall down. And so, as a rule, as a default, we want programmers to guard stuff that could fall down with graceful handling. So Java and other, not just Java, but other languages say you must write an exception handler whenever you write code that could do this. Okay? And so anytime that happens, this could arise. Let's keep moving. I'm a little bit conscious that we're running out of time here. So what we could do now, I want you to tell me what you think is going to happen now. I'm going to do something else here. Int I equals 7 divided by 0. All right, so what should happen now? Can anyone tell me what's going to happen now? Anyone? What's going to happen when I run this? I've just added something bad here, right? So it's divide by 0. That's bad. Okay, so what should happen when I run it? Divide by 0 exception? Math error? No, interestingly, not. Oh, what? Oh, yes, sorry. You guys are right. I just wrote my code wrong. That's not what I meant to do. Dang. What I meant to do is that. I've spoiled the punchline now. So the code was supposed to be written right after there. Okay, so let's just run it again. This is what I was trying to demonstrate to you. Okay, this is the point I was trying to make, right? So now what happens is the exception gets handled here, and this is a different exception. This is the one we saw before with a null pointer exception. And so that line of code never gets executed. So we never see the divide by zero error with the code written the way I have it now, okay? You're absolutely right. The way I had it a moment ago, of course, this code was before. Let's just make it really obvious to everyone. We'll put it right up here. And now what should happen is it will fall through here and get the exception at this line, and we won't get the other one. We can be clear about that by doing the following. Put a null pointer exception like this. Like that. Now what we're doing is we're catching these two different, we're very carefully catching null pointer exceptions, like this, like that. And we've got an arithmetic exception instead, right? So what's happening is when that happens, it goes here and says, do we have a null pointer exception? No, it's not it. But the exception here is generic. It catches not generic. It's the superclass, so it'll catch everything else as a catch-all, if you like. Okay, so when the exception happens here, it falls through. It doesn't match that one, so it matches this one. So it gives us this arithmetic exception. Okay, and prints that out. We could write another clause in here which looks for arithmetic exceptions, and it would print that out as well. Okay, and if we put this back again the way we had it, like this, like that, and run this, then what we should find now is that it prints out the null pointer exception, which is this. Notice the error message is this one. Okay, and what we can do now, the last thing I wanted to do here is to add in the finally clause, and then you can say and what we'll see here is that even when the exception happens, the code in the finally clause gets executed. Okay, but notice the okay, so with the null pointer exception up here, so even though this doesn't get executed, this does get executed. Okay, so the finally code gets executed as well as the exception handling code, and it's guaranteed that this will always get executed no matter which exceptions happen up here. Okay. I think I want to move on at this point, unless there's something else. What I want to do now is I want to flip back to the code we had in AO2. And what I'm going to do again is some gratuitous copy-paste. Dump this in here. Paste them in there. What we're going to do now, actually, yeah, I will do it that way. So what we're going to do now is we're going to go to our tests. We're going to add tests to check. So I'm just catching up with the chat. How many can you catch? You can catch all different kinds of errors. The code. Yep. Sorry. Look, I need to move on. What I need to do here is what we're going to do. Right? Is we want to remember when we wrote our lists, we wrote tests. One of the things we want to test for is whether or not our code correctly generates exceptions when it should, because something like a list should generate exceptions if the user gives bad input. Okay, so what we're going to do now is we're going to actually do that, and the way you can do this is we can do the following and say at test, and then we can put in parentheses expected. There you go, equals what we'll do is we'll do a test for get and make sure that get throws an out of bounds exception when it gets a value which it shouldn't have, like -1 or something that's bigger than the size of it. Okay, so what we can do is index it. There we go, index out of bounds exception. So we're expecting this thing to throw an index out of bounds exception. I need to include this like that. Whoops. Sorry, hang on a sec. We're going to write public void. We'll call it get test get empty. So we're going to try and get something empty, right? So what we're going to do is we're going to create a list, not put anything in it, and then try and get something out of it, which should give us an index out of bounds exception. Oh, actually, this should be a class, dot class. There we go. That's what's happened. That it should return an object of that type. Okay. Now what we're going to do is we're going to say get empty. So what we're going to do is create ourselves a list like this. Same code here as this. Cut and paste. And then we're just going to call get on it, even though we haven't put anything in it, right? So we say l.get, and we'll get 0. Okay, and that should fail because we haven't implemented. If you remember from when we did this code, we did not actually implement this stuff, all right? So that should fail. We run the test now, and our tests were all passing. Oops, wrong thing. Test run. Okay, so run the tests. Okay, so all the tests were passing. Now we've got a failure here because it expected this, but it got a null pointer exception. Okay, so it got the wrong kind of exception. Okay, we got a null pointer exception. This should not give a null pointer exception. It should give an index out of bounds exception. Okay, because we do have the list. There's a list there, and we're trying to get element 0. But our code, the work code we wrote, is giving a null pointer exception, which is not what it should do. It should give an index out of bounds exception. Okay, so let's just do a few more of these. We'll do the same for remove, just exactly the same thing, but for remove. Cut and paste. Test remove empty. And then say remove 0. Right, and that's bound to fail the same way, or something similar. Then what else can we do here? This is where I really love to have it interactive and ask you guys some for suggestions. One is where we go too far, so we try and get something beyond the end of the array. Okay, so we'll add something and then ask for the thing after it, which should also create an exception. So we'll call that overflow, and we can essentially do the cut and paste this same stuff here, because we want to do it for both get and for remove, and we'll call it overflow. That was empty. We'll call this overflow. Okay. And what we'll do is we'll add something in here. L.A. We're going to put A in this, and there is actually something in there, but we're going to, if we say get 0, that should be fine. But if we say get 1, that should not be fine, because there's only one element, and get 1 would be getting the second element, so that should not work. And we'll do the same thing here. L.add A, and then we'll say remove 1, which again should generate an out of bounds exception. Okay, what else can we do? Oh, the other obvious one we can do. Anyone got another suggestion? You have test get over. Okay, sure. Thank you. Over low. All right. One more thing. So we've done empty when we access an empty thing. That's not going to work. We've done when we accessed beyond the end. There's one more thing we can do that's really obvious, and that is to access a negative in negative number, right? So let's just do that as well. So cut and paste this code, and we'll just call it under. We call it underflow. Okay, and then we'll say all right, so now we're going to try and access the negative thing. What else did I have? Do I have any other suggestions? That will probably do. Okay, so let's get on with that. Let's try and do it. And it should all fail, right? There you go. So all the ones we just added were all going to fail. So now let's get into that code there, and we've got linked list first. So where is this? This should be in a in remove. Okay, so what we want to do now is we want to in the remove, hang on, what we want to do is in the remove we want to say if the index under what circumstances should be thrown out of bounds exception. If it's less than 0, it should throw out of bounds, right, because it's a negative number. Or if what, under what other circumstance should it throw out of bounds? So it's if it's under, or if it's greater than the number of elements in the list. Okay, so let's just do that. We'll say if index is less than 0 or index is greater than or equal to elements, like that. Yeah, no, yeah, size of the contents of the list, not size of the array in the array list. But yeah, exactly, greater than size, someone says. So if that's the case, then what we're going to do is we'll throw our exception. Throw, oops, throw new index out of, oops, man, typo, index out of bounds exception. Okay, like that. And we're going to do the same thing for get. Where's get? There it is. So we'll do the same thing in here. And we'll run this. And now our linked list should, hopefully our linked list will pass. Great. We just fixed all those errors. Okay, we now need to go and do the same thing for our array list. Remember that this test did both. So we're going to flip this over. So it's testing our array list. True. So let's test the array list now. And we run the test and it should all fail. Let me see people saying stuff in the chat here. Yeah. All right. Okay, so now the array list did fail, right? It failed all those remove ones. And let's just add the same thing in there. And I'm going to be really lazy because we are really short on time here. We're going to copy that code there from get and put it in the array list. Its get's going to do exactly the same thing. It needs to check before it returns a value, like that. And then we can do the same thing for remove. Okay, and run the tests. Great, so we've passed. Okay, I want to quickly recap that what we've done here is I just introduced you to the idea of exceptions. You're vaguely familiar with them because we've bumped into them the way Java works. You had to bump into them before. I've now explained to you how they work, why they exist. You put them there to make the programs not fail, or at least to handle exceptional circumstances in a relatively graceful way. Okay, and I explained to you the Java rules about catch or specify, and I explained that there are 3 types of error. There were the 3 types of exceptions. There were the errors, there were the runtime exceptions, and then there were the other ones. And the last category, anytime one of those is going to occur, you have to have a try catch there, or you have to specify the method is going to throw an error. I then gave you a small example program where we generated exceptions by writing bad code that like divide by 0 or null pointer exception, and we handle those exceptions. And then we went and I showed you how we can add tests to test whether our code correctly generates exceptions. Then we went and added exceptions to the array list and to the linked list. Now let me just go back. There's something I think I may have not done. Did I do it in the end where, yeah, one thing I didn't do is, one thing I meant to do here is to, is if we have the exception, maybe I did it before, but if you have something like this, we'll put J here and make it J a different value. Go back to this piece of code here. If you do this, what should happen is this stuff has no effect, right? Because the error, the divide by 0 here, is happening outside of the try catch. So what should happen? Well, it should just print start of method, then it should fall straight back to here. And this will find that it can't catch it, so it'll then die at this point. So let's just run that just to be clear, so everyone sees it. Oh, wrong one. Exceptions. Run this. Okay. It says divide by 0, and it happens after the start of the method, but it never gets to print this out. Okay. And the error just doesn't get caught. It crashes at this point, and we don't see this being printed out. We don't see this being printed out. Okay. And I'll just comment that out. So if you wanted to look at the code later, you can go and mess with that. Now, finally should be called to write. Not sure what that means. All right. I think we're done there. Now, I think what we can do is I wanted to, I need to jump out of here and go back to our other slide deck. Sorry about that goof up before. And it's too late now to jump into this, but that's only a few minutes, and it's like only 6 or 7 minutes worth of stuff. So we'll just jam this into the front of the next lecture. Hopefully we'll be fine with that. And what I'll do is go to our bio. Ken Thompson. Ken Thompson is another one of the great computer science luminaries, and he is most famous for his role in the development of Unix. Okay, but he did a number of other things, and most particularly, he's the person who invented a language called B, which you've probably never heard of. Many of you have never heard of B, but you've probably heard of the language which came after it, which is called C. And this is not a joke, this is for real. He made the language B. And both of those languages were built, Brian Kernighan and Ken Thompson were involved in, and Dennis Ritchie were involved in this effort to build a language called Unix. And they wrote, and Dennis Ritchie and Brian Kernighan wrote the language C. And C ended up being the language that was used to implement Unix. B was intended for that purpose, that they might use it to implement Unix, but they didn't in the end. They end up using this other language called C, which was written by Dennis Ritchie and Brian Kernighan. And Ken Thompson is also famous for having developed regular expressions, being one of the key people behind regular expressions, which we use a lot in computer science, and for developing the UTF-8 character set, which is something we use, which standardizes the way we represent characters on computers. He did many more things. His main claim to fame is actually in operating systems, but he was also famous for inventing the language B, which is the precursor to C. And now, was there a language A? No, there wasn't, as far as I know. There was a language called Algol, though, which is related, and I think surely it comes before them. I should know this in terms of computer history, so I'm pretty sure Algol came before B and C, and that maybe that B is a reference to Algol being A. All right. Any questions? If they're not, we'll finish up now. In the next lecture, hopefully I'll get the Zoom working. I've worked out a way. I think I've worked out a way to throttle the bandwidth that Zoom's consuming, because unfortunately Zoom will gobble as much bandwidth as it can, and what it does is it steals the bandwidth from my streaming service, which is why when I was using Zoom in the last lecture, the streaming suffered because Zoom is very aggressive, and there's no way in Zoom to turn that down. But I think I found a way to throttle it on Mac OS. Yeah, that's right. There are ways to do it, but not inside of Zoom. I have to limit how much that particular port gets. Anyway, ugly technical stuff, which I shouldn't have to worry about when I'm giving a lecture, but it turns out I do when I'm doing remote learning. And but my intention is to get Zoom working, so that, because I think that you'll find it more fun when we can actually do proper interactive stuff, when I can hear your voices. With that, I think we've finished the lecture, and have a good weekend, and I'll catch you on Monday.